Okay, let's just do another one. Let's say that we run an experiment for sodium using 500 nanometer light and find that experimentally the stopping potential is 0.2 volts. What is the maximum kinetic energy of the photoelectrons? What is the work function of sodium? And then I'm asking a qualitative question, what happens to the photocurrent if I use 600 nanometers instead? And what happens to the photocurrent if I turn up the intensity of the 500 nanometer light? So you remember that the stopping potential gives you the maximum kinetic energy, and also the maximum kinetic energy gives you the energy of the light minus the work function. So it is, part A is simply a plug-in into E times 0.20 volts, and you can plug in 1.6 times 10 to the minus 19 coulombs for E, but that would be silly because it's 0.20 electron volts. And it's pretty easy to go from there to 0.20 electron volts equals HF minus the work function. Therefore, the work function must equal to HF minus 0.20 EV. Then did I just say this? The work function is HF minus 0.20 EV, and just aside, let's go ahead and calculate HF is HC over lambda. That's the wavelength of the light that we're using, because I gave it as a wavelength, not a frequency, and we know that HC, we had already calculated, is 1.2 times to the minus 1.2 times 10 to the minus 6 EV, EV meters divided by 500 nanometers. HF is 2.4 EV, so that means the work function is 2.2 EV. The work function of sodium is 2.2 EV. Let's hope that's right. I don't know if I chose those numbers correctly. Now we go to part C, which says what happens if I use to the photocurrent if I use lambda equals 600 nanometers instead. Now that is a higher wavelength, therefore it's a lower frequency, it's a lower energy light. So that means that it would give us electrons with less energy, which would reduce the photocurrent, but we do need to check if that's above the threshold frequency, because it may be that that turns off the photocurrent. So I think that qualitatively we probably need to just figure that out. So that the threshold frequency, remember, of course, is or the threshold wavelength is HC over lambda 0, and so we can solve for lambda 0, and we find the cutoff wavelength is 545 nanometers. So if I go up in wavelength any more than that, there is no photocurrent. So the answer to part C is the photocurrent turns off. Answer to part D, what happens to the photocurrent if I turn up the intensity of the 500 nanometer light? Don't be inclined to say nothing, because it doesn't increase the energy of the electrons, but increases the number of electrons. Remember, these photons, what happens when you turn up the intensity is you're turning up the number of photons, and so that means that they can release more electrons. Think of collisions between photons and electrons, 1 to 1. Each time a photon hits an electron, it releases it. You got more photons, you got more electrons. So even though it doesn't give them any more energy, it does increase the photocurrent. So the photocurrent must go up if I increase the intensity of the light. Okay, that's all I got for photoelectric effect. Moving right along.